Hello everyone, I am Karthik, Assistant Professor of Mathematics, SNS College of Engineering. In this video, I will explain about what is ordinary differential equation, how to solve ODE and some applications of ODE. Okay, what is ODE? Ordinary differential equation are equations involving functions of one variable and their derivatives. They describe how functions change with respect to that variable. The general form of ODE is d power n y by dxn plus k1 into d power n minus 1 into y divided by dx power n minus 1 plus etc. kn into y equal to x, where k1, k2, etc. kn are constants. D is the operator, that is capital dy equal to dy by dx, differentiation of y with respect to x. D square y equal to capital D square y equal to d square y by dx square, that is second derivative of y with respect to x. Generally, d power n y equal to dn y divided by dxn. Solving first order ODE. First one is separable equations. Separation of variable is a technique used to solve certain types of first order ODE. It involves rearranging the equation so the all terms involving the dependent variable are on one side and other terms are right side. For example, given first order ODE is dy by dx equal to 3x square by 2y. Separate the variables by moving terms involving in y to one side and terms involving x to another side. Then it will be 2y dy equal to 3x square dx. After that, integrate on both sides, we get the solution. Exact equations. Exact equations are specific type of ODE that can be solved using technique called the method of exact equations. The equation typically take the form m of x comma y dx plus n of x comma y equal to 0, where m and n are functions of both x and y, that is dou m by dou y equal to dou n by dou x. Integral m dx plus integral n dy equal to some constant c. Linear equations. Dy by dx plus py equal to q, where p is constant, q is constant or functions of x. Next, some applications of ODE. First one, population growth model. Differential equations are used in population growth models to describe how population changes over time. The simplest model is logistic growth model. The model can be represented by the differential equation dp by dt equal to r into p of 1 minus p by k, where p is the population size, t is time, r is growth rate, k is capacity. The equation describes how the population p changes over the time t based on its current size. Next, electrical circuits. Differential equations are fundamental in describing the behavior of electrical circuits, especially when analyzing dynamic systems or circuits with varying voltages and currents over time. By Kirchhoff's law, the first order differential equation dv by dt equal to 1 by r into c into v in minus v. V is the voltage across the capacitor, V in is the input voltage, R is the resistance, C is the capacitance. Spring mass systems. The differential equations are extensively used to model the behavior of spring mass systems, which are commonly encountered in physics and engineering. The equation of motion for spring mass system can be derived by Newton's second law. The following second order ordinary differential equation is m into d square x by dt square plus kx equal to 0, where x is displacement of the mass from equilibrium position, t is time, m is mass of the object, and k is the spring constant. Numerical methods for solving ordinary differential equations. First one is Euler's method, second one Runge-Kutta method. The Euler method is simple numerical technique used for solving ODE. How the Euler method works? Start with an initial conditions, that is y of t0 equal to y0, where t0 is the initial time. Next, choose the step size, that is del t. The formula for updating the solution using Euler's method is yn plus 1 equal to yn plus f of tn comma yn into del t. Yn is approximation of the solution at time tn. F of tn comma yn is the value of the derivative of the solution function at time tn and yn. Del t is step size. Yn plus 1 is updated approximation of the solution at time tn plus 1 equal to tn plus del t. Repeat until you reach the desired endpoint. Next one, Runge-Kutta method. The Runge-Kutta method is numerical technique used for solving ODE numerically. How Runge-Kutta method works? It is also start with an initial condition y of t0 equal to y0, where t0 is the initial time. Next, we have to choose a step size, that is del t. Third one, iteratively approximate the solution at each step. First, calculate the slopes k1, k2, k3 and k4 using the following formulas. k1 equal to f of tn comma yn, k2 equal to f of tn plus h by 2 comma y1, yn plus h by 2 k1, as well as k3 and k4. These are the two methods for solving ODE. Thank you.